Hi everyone, my name is Eduard Zingerman. I'm working on the BPF verifier in Linux kernel. And this talk is not GCC related, but we are hoping to get some feedback from the compiler experts in the room. So, yeah, our main issue, like one of the main pain points in the verifier right now is that we are limited in our capability to verify loops. And in this presentation, I'll show what I mean by that. And we are constrained by a need for real value range analysis, which can predict induction variable ranges and so on. Yeah, so first, an overview how mechanically a BPF verifier works. So verifier represents the program state as a current stack frame number, a stack of stack frames, of all stack frames, each having an instruction pointer, register values, and stack slot values. And we are lucky in the sense that there are very strict constraints on the size of the state. We limit the state of the program to 8 stack frames. There are only 10 registers, and there are only 64 8-byte stack slots per frame. And at the beginning, basically, BPF verifier, it's a simulation machine, abstract interpretation machine. It starts from initial states and then mutates it forward. So the initial states, in the initial states, one stack frame is allocated, instruction pointer is set to the entry point. R1 contains a pointer to the context, which is a parameter passed to BPF program, be it some data about network packet or something like this. R10 is set to a frame pointer, and the rest of the registers and frame slots are marked as uninitialized. And then exploration proceeds in a depth-first search manner, and we maintain a stack of unexplored states. So instructions are simulated sequentially. When the program exit instruction is met, current path exploration completes, and we pick the next state from the unexplored stack. When jump instruction is met, we fork current state, and we continue through the false branch, and state for the true branch is put onto the stack. And ranges for variables, if those can be inferred from the jump condition, are adjusted in the current and forked states. And some more limitations, if we simulate more than 1 million instructions in this way, we give up and reject the program. And if the backlog of unexplored states is bigger than 8K states, we again reject the program. Verifier also employs state pruning, state caching mechanism to make this thing work a little bit more robust. So basically, we maintain a hash table where the key is a current call chain and instruction pointer in the current frame to the state, actually the list of states. It should be a list of states. So at certain points, we call these points prune points, and these points currently are call instructions, some, and jump instructions and jump targets. We look up this hash table in a search for a state which can be considered to be a super state of the current state. And if we can find such state, we stop the traversal of the current path and continue with the next unexplored path. If we cannot find a super state for the current state, we fork current state. We put forked state into this hash table, adding it to the list, and proceed verifying the current state. So while at it, we maintain link, like backlinks for the forked states, so that we see the complete tree of the states currently under exploration. And the reason this tree is necessary is to mark like when all children of a certain state have been processed, have been verified. And the idea is that when all children of some state had been verified, it means that the states lead to program exit. And we can assume that this state is correct. When we can assume this, we can use it in this comparison mechanism when we are looking for a super state for current state. So in order to increase our chances of finding more this super state, we prune the states which we put to the hash table by removing dead register and dead stack slots. So for dead registers, everything is pretty simple. We just do a classic liveness analysis on the control flow graph and mark for each instruction in the program what registers are alive. And then we use this information when we put the state into the hash table. For stack slots, it's a little bit more. An old mechanism for this was that whenever verifier sees a store instruction, it marks current state as writing to a certain slot. Whenever it sees a load instruction, it propagates the read mark up the parent chain of the states. And eventually it accumulates these read marks for stack slots on all states in the current exploration tree. And the reason we don't use regular data flow analysis for stack slots is that we cannot run it during without the main simulation pass. If we alias stack frame, we need to know that in this example R1 is a stack frame, and we need to know also the value of R2. And this information, oh sorry, I missed an addition. R2 should be added to R1. Yeah. So the information about the range of R2 and R1 and the type of R1 is available only during main simulation pass. And this is when we also want to know this information about live and dead stack slots. When a state cache hit is found, we also connect the read marks from the cache state. Suppose we have a chain of states A, B, C, D, and at some point we also forked an unexplored state E. And then we find that the current state is equal to some state D. So this is a cache hit. So we take the stack slots which are marked alive in D and propagate this information up the chain to E and to A. Now, about loops. So the simplest form of loops verification is just brute force. So this loop will be verified 100 times, which is obviously, well, it works for small loops. The next form representing the loops is named iterator-based. So basically we have a concept of iterator, and most important function for it is next. And the contract is that implementation of function next and on the kernel side will eventually return null. So, and at the next function call, verifier forks the state, and in one branch it emulates the exit, the null returned by next, and proceeds through the branch and proceeds in the state. And on another branch, it simulates another iteration of this iterator. And contrary to normal state caching rules, verifier is allowed to prune states at next and at call to next even if the state against it, like if we can find some superstate S, and we see that this exploration of this superstate is not yet complete. So basically, we are like in a DFS and we found the back edge. For the we are allowed to stop this path traversal, but we cannot use the read marks for state when comparing states for substate relation. And what this means is that, like in this diagram, we cannot propagate this information back because it is not yet complete. And to work around that, for loops, we just accumulate the complete state graph inside the loop. And when the finally the state which first entered the loop, exploration of the state completes, we propagate the read marks on this graph until fixed point is reached. And like this works somewhat against our goal in a hash table. So the hash table has is actually a hash because we don't want to keep all of the states we ever explored in the hash table. We want to keep only those states for which we can see some hits on the path traversal. So we essentially evict some of the states from this cache. And while we are in the loop, we cannot evict states which are part of this loop, which leads to increased memory consumption. Yeah, so first thing we are working to get rid of is this state graph accumulation. And in order to avoid it, we want to work on the control flow graph. And yeah, basically, we recently replaced the before mentioned stack slot liveness mechanism with context-sensitive analysis. But because we still depend on the main simulation path to provide us type information and range information for variables, this context-sensitive analysis is effectively run multiple times. So we maintain like a map from and the key in this map is a current call chain and current instruction to a set of like may read, must write, live before, must write after marks. And while we proceed with simulation, may read and must write marks are accumulated for the instruction in a certain call chain when stores and loads are processed. And when we actually need to query information about whether some stack slot is live or dead, we initiate the read marks propagation. And we do this in the post orders for all the call frames. So we first process call chains which are leaves, then we proceed with call chains which are colors of these leaves, and so on. And to propagate this information between call chains like callers and call leaves and callers, the live before information from the entry point to a subprogram is transferred as may read information to the call instruction in the appropriate call chain, and same happens to must write after marks. And yeah, so the next step is we want to have these read marks available when we do cache pruning inside the loops. And for this, we need to actually reason about this program in terms like what might be the value of R2 had it been here like a plus instruction, I'm sorry. And for this, we need some value range analysis. And yeah, another use for it is we want to use it for induction variable bounds in order to do some widening when we process this next call. And the question to the auditorium is, I need some links to algorithms and papers I should look into.
Well, I will look maybe into the corresponding GCC pass. I'm not familiar with the GCC passes that do value range, propagation, but I guess that would be a good start for it.
Well, yeah, I started to look at scalar evolution analysis as it's implemented in LLVM. I suppose GCC uses something similar, but I don't know.
I don't know. Do we have any middle end expert here?
Yeah, Andrew McLeod didn't come to Cauldron, and Aldi is retired.
Yeah.
They are responsible for emails.
Yeah, yeah, because they worked on the Ranger infrastructure, so they'll be the best.
Andrew's working on the docs and looking as well. Functioning a lot more. Yeah, Ranger is like the keyword, and Aldi is.
Well, we can give you those contacts, get you in touch. But do you have any more concrete question, or just the idea is okay how to approach this from a general point of view?
The problem is papers are about SSA form, and we don't have SSA form. The program is assembly.
Well, yeah.
Yeah, and the papers assume that you infer this information only for variables, not variables but values on this SSA. But I want it also for stack slots. So there is some extensions here. But I can describe the problem in more details when contacting the people.
The value range analysis that we do is on SSA, necessarily, yeah.
No, because the theoretical underpinnings are all based on SSA.
That's the
Yeah.
sort of missing out on a whole set of research. There's a reason why we use SSA, right?
So you may be in uncharted territory.
Okay.
GCC adopted it fairly late.
Yeah.
We're very glad we did.
Yeah, GCC's adoption of SSA was late, and it was static and IBM and stuff, because all of the theoretical,
I think Sam was saying GCC was a late adopter to single static assignment, but the theoretical underpinnings allow you to then write all the algorithms on top of the proofs that you have for SSA. GCC adopted it late in I remember GCC Summit in Ottawa when we were discussing SSA. Yeah. But yes, so you miss out on a bunch of just foundational papers that you can't employ because you don't have the foundational underpinnings for the formalized model that SSA gives you. But I feel like you have to be able to do some things here. And if Andrew McLeod was here or Aldi Hernandez were here, they'd have answers for you. So I do think we should just reach out to them.
Yeah. Maybe we could organize some sort of call, maybe in a BPP or something.
Absolutely, yeah. Or do toolchain office hours. I can ask Andrew to come. Andrew McLeod's in Toronto, so he's EST time zone, so he can show up. What's your time zone?
Vancouver, Pacific.
Oh, you're Vancouver Pacific?
Yeah.
Yeah, we'll just have an impromptu meeting, I think, if you want to talk.
I mean, whatever the time is, I can get up early.
Would you like that? You can do that.
Yeah, I can ask Andrew. Andrew's on our team within Red Hat. He's on vacation right now, maybe. So we might have to wait 10 days, maybe.
That's fine. That would be awesome. Thank you.
Okay.
My memory is a little bit rusty, but I think LLVM has a... Sorry. My memory is a little bit rusty, but I think that LLVM has a special pass to take memory references and convert them to SSA form. So maybe you can use that, and if your input is pretty simple, convert everything to SSA, and then there is another path that does value range analysis in LLVM.
Okay.
But this is the verifier, right?
Yes.
So it's...
Well, that's a problem, but you can take the source code of those two passes and run with that. So this is called mem to rec pass, and there is another value something pass in LLVM.
So could you please repeat that? I will write down the passes.
Sorry?
Or I will just ask you. I will just ask you after this thing.
I can just come to you after the talk.
Okay. Okay. Well, then that's all I had.